Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai. Welcome back, everyone. Today we're jumping into a 9th grade topic, rationalizing your denominator. Now, if you're new to my channel, I'll be putting timecodes in for this video in the description box below, so use that to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions, anything whatsoever about what you see here today, or even your own homework, feel free to either put in the comment box below or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. Now, today's video shouldn't be too long, so hit that like, smash the subscribe button, and let's get started. Now, today's video builds upon what we've already talked about, and we've talked about a few things so far. We talked about what a radical is, we talked about how to simplify constant radicals, how to simplify radicals with variables. We've even talked about how to multiply your radicals. This video is going to be kind of using a little bit of everything that we talked about and building upon that to go to the next step. So if you have any question about any of those topics, I have a video on each and every one of them that you can find right up here. So check that out if needed, and then come back to this one just to make sure that you've gotten your building blocks in order. But if you have everything in order that you need, then let's move on to our next part of this video. Before we jump into actually rationalizing our denominator, why do we even rationalize our denominator? If you don't know that question, there's a few different reasons why someone would ask you to rationalize your denominator. For example, your teacher. That person may have a few different reasons why they want you to rationalize your denominator, ranging from making sure you simply know how to do it to just making it easier on themselves to actually grade tests. So if you see a bunch of people with something like this, and then some other people have something like this, well, how do you know at a glance that these are the same answer? Well, that's why you have them choose one. And by choosing one, then you can just focus on the one that you're looking for, making things so much easier to just visually tell if something is wrong. If you have two options, you have to kind of switch in your brain. Okay, this is good. But if you have only one thing you're looking for, if it's not this, then it's going to be wrong. But let's say we go beyond your teacher. Why do we even rationalize at all in general? Well, before calculators were a thing, rationalizing the denominator made calculating these fractions a little bit easier. Instead of dividing by something that was irrational, you can divide by something that is rational, and it's a little bit easier. We have calculators now, so this is kind of a moot point, but since long ago we were doing stuff like that just to make sure that we don't have to do more work than we necessarily have to. On top of that, we don't typically have a ton of radicals in our denominators in everyday math. You're more likely to find a constant in your denominator than you are to find a radical in your denominator. So because of that, if you had to add or subtract any kind of fractions, typically you're going to have to look at them with a constant. So if you had these two fractions, you would have to do more math anyway in order to combine them, to even see if you can combine them. Whereas if you automatically simplify this or rationalize your denominator, at a glance you can easily tell if you can combine them or not and what kind of extra work you have to do. So rationalizing your denominator for just regular math makes it easier to look at and to use. Similar to just simplifying anything that we do nowadays. You simplify your fractions to make them easier to use. When you have really big fractions, simplify them. When you have big polynomials, you simplify them. We just like to make things a little bit easier to work with, and rationalizing your denominator is one such way. So in this video, I'm going to show you 3 different types of denominators, 2 of which you're probably more likely to run into, and that last one is kind of a bonus just to throw in. Each of the 3 denominators will have a different difficulty when you're trying to rationalize them. So let's start with the simplest one first. So when I was breaking up these 3 denominators, I actually reminded of one of my favorite scenes in one of my favorite childhood animes, Dragon Ball Z. And that is when Goku was actually breaking down his transformations to Majin Buu. When he met him, he was in his normal base state. So I want to actually have some equivalency here. if you're going to be simplifying any of these radicals, that's going to be your base state. That's probably what you're going to run into more often. What you're going to see here are going to be these Super Saiyan levels. Now don't get scared. We can still tackle each and every one of these, but I want you to know these are probably going to be a little bit more work than your regular simplification of your radicals that we've talked about so far. So once again, if those were our base forms, our regular radical simplification, this is going to be your Super Saiyan.
You're going to love this. Trust me. What you're seeing now is my normal state. This is a Super Saiyan.
So we have this fraction here, 1 over the square root of 2. And we want to rationalize this. Now, this is going to be the simplest one. And I say it's the simplest one because all you have to do, because we have a square root here, is multiply top and bottom by this same square root. By doing that, you're going to get the square root of 2 over 2. And that's because we already know how to multiply radicals, right? When you do the square root of 2 times the square root of 2, you get the square root of 4, and the square root of 4 is just going to be simply 2. Notice that you no longer have a denominator with a radical. That is the whole point of rationalizing your denominator, to remove the radical from the bottom. So whenever you're dividing by a square root, all you have to do is take that same exact square root and multiply top and bottom. We do this so that we're multiplying by 1 and we're not changing the value of our fraction. We're just changing how it looks. So this is the simplest one. However, just because it's simple doesn't mean that all of them are going to play out the same way. Let's say instead of the square root of 2, we have the cube root of 2. Remember, the goal of rationalizing your denominator is to remove the radical. If you were to take the same exact approach and you multiply by the cube root of 2, top and bottom, what will we get? So we would get something like this. The cube root of 2 over the cube root of 4. Does anything actually go away from the denominator? No. Why is that? That's because 4 is not a perfect cube. So what we want to do is actually not just simply multiply by what's in the denominator. We want to have a strategy. We want to figure out what we need to multiply by in order to make whatever's in here a perfect whatever index this is. So when this was a square root, the index was 2. So we want a perfect square. When this is a cube root, we want a perfect cube, and so forth and so forth. So you see that simply multiplying by a 2 is not going to make what's in this radicand, a perfect cube. We have 4. We need to do this again. And by doing this again, we're going to end up with the cube root of 4 over the cube root of 8, in which we can simplify the cube root of 8 now to be 2. So you see, we had to do it 2 times. Now, you don't always have to do it 2 times. So let's back up a few steps. So let's say instead of working harder, we want to work smarter. We know now that we want to get whatever this is, this radicand, to be a perfect whatever this index is, a perfect cube in this case. So we know that instead of multiplying by the cube root of 2, which is not going to get us what we want to multiply by something that's going to make that radicand special for us. And that radicand is going to be special when it's an 8. So what do we have to multiply in order to get that 8 there? Well, that's going to be a cube root of 4. So you see, we just do it all in one step, and then we get the same exact answer we just got, and then we can simplify it. So you don't even have to do this step, because you know that whenever you multiply these two things together, you're going to get that perfect cube. That was the whole reason why we chose this number in the first place. So you're going to get that perfect cube, so you could technically skip this step. However, to not confuse anybody, I wrote out all the steps here. So you see, we can work a little bit smarter, knowing where we're trying to go and not just multiplying blindly just because you have this. And this is going to be true for the 4th, 5th, 6th root. It doesn't really matter. As long as you know where you're trying to go, you can multiply your top and bottom by that same radical to get you where you need to end up. The square roots are going to be the simplest because it's literally multiplying by the same denominator you already have. However, for higher roots, you're going to have to do a little bit more thinking, a little bit more legwork. But it's still pretty simple because you're multiplying by one thing, top and bottom, once you figure it out. So we've handled our Super Saiyan version of what we were talking about. Now we're going to bump it up a notch, right? We can go a little bit beyond Super Saiyan. This would be equivalent to our Super Saiyan 2 of the bunch.
And this This is what is known as a Super Saiyan that has ascended past a Super Saiyan. Or you could just call this a Super Saiyan 2.
Now the denominator looks special here, right? We can't just simply multiply top and bottom by some radical because we're going to have to distribute that radical to both parts of this denominator. And by doing that, we're going to introduce another radical. Although we might get rid of this one will now have a radical. So therefore we wouldn't be rationalizing the bottom because we still have a radical there. This is when we introduce another concept called the conjugate. So instead of multiplying by a single radical, we're going to be multiplying something that we call the conjugate. Now what is a conjugate? So let's say you have this binomial here. The conjugate is going to be the binomial that you have, except you're going to be swapping the sign. So just simply put, it's going to be the binomial with the opposite sign. So in this case, our binomial is going to be 2 plus the square root of 2. So our conjugate is going to simply be 2 minus the square root of 2. And you're going to be multiplying top and bottom because we still want to multiply by 1. Now, why do we multiply by the conjugate? What is so special about this conjugate that it's going to be the key for attacking our Super Saiyan 2 version? Well, if you recall, FOIL, your first, outer, inner, last, when you're multiplying these two binomials, you're going to have to do something for the outer, inner. Having that opposite sign assures us that the outer, inner is going to cancel out. And we can check that out. So let's say we have 2 plus the square root of 2, 2 minus the square root of 2. We're just going to focus on the outer, inner. So the outer is going to be this. And the inner is going to be this. So what's the outer? That's going to be 2 times this negative square root of 2. So it's going to be a negative 2 square root of 2. What's the inner? That's going to be a positive square root of 2 times a 2. So it's going to be a positive 2 square root of 2. And what happens when you combine these two things? Well, you see, it's the same exact value except they have opposite signs. That means they cancel out. That is the beauty of using your conjugate. Your outer inner is going to equal 0 when you combine them. That guarantees that we have no extra radicals because our first is going to end up with a square and our last is also going to end up with a square. So there's no possible way for us to still have a radical when we're dealing with these square roots. So let's clean this up and see what our actual math is looking like. We want to make sure we're using the conjugate, and we're realizing that we can just skip the outer and inner because it's going to go away. So let's just focus on our first and last part of FOIL. So once again, we want to multiply by the conjugate. The conjugate is going to take our binomial and switch the sign. And we do top and bottom to make sure we're multiplying by 1. And when we do that, we get 2 minus the square root of 2 in the top because we're multiplying by 1 here. And for this, we're going to just focus on the first, which is going to be 4. And then we're going to focus on the last, which is going to be 2. And you see our sign is going to make that a negative. Now we can simplify this to be 2 minus the square root of 2 all over what? 4 minus 2 gives us 2. This is going to be our answer. Now this is a 2 here. So the takeaway for this Super Saiyan 2 version is whenever you have a binomial that looks like this, especially with a square root or only technically with a square root, we want to focus on the conjugate. That conjugate allows us to ignore our outer inner because the math is going to cancel out to 0. And in doing that, we guarantee that there's going to be no possible way for your radical to still remain in the denominator once you're done. So at this point, we've covered our Super Saiyan 1 and our Super Saiyan 2 version of denominators that need to be rationalized. Now we're going to the behemoth of the bunch. This is what I would call Super Saiyan 3.
And this
What's he doing?
is to go even further beyond.
Now, I don't want you to get scared off by this hard here. Yeah, the first two were simple and medium, but that's just letting you know, just on average, how much work you're going to have to put into it. This is going to be a little bit more work than the previous two. And that's because instead of having our radical here be a square root, it is now a cube root. There's a little bit more that we're gonna have to do in order to get this cube root out of the denominator. Now you might be wondering, why can't we just use the conjugate like we did for our previous one, our Super Saiyan 2? Why is this different? Well, this is going to fall into the same trap as to why you couldn't just multiply this top and bottom by the same exact radical. When you multiply this, it's not going to go away. 4 is not a perfect cube, and neither will 16 be. At the end of the day, you're still going to have a radical in denominator because you're not getting rid of your radical. If you ended up using the conjugate, you're just simply going to be multiplying this cube root of 2 by cube root of 2, and you're going to get a cube root of 4 here. That is not a perfect cube under the radical. So this one is going to take a little bit more thought in how to approach it. Now, truthfully speaking, you're probably not going to run into this very often, if at all. But hey, if you're curious and you want to continue watching this video to figure out how to attack this, just stay tuned. All right, if I still have your attention, let's attack this. We want to use our minds in such a way where we see the future, right? And when I say that, we want to figure out where we are trying to go. Ideally, we want nothing with a radical here. Well, in order to do that, this needs to be cubed. So let's rewrite this in very simple terms using variables so we know exactly what we're looking for. So this is going to be a 1 over, let's say, a plus b, in which a is going to be 2 and b is going to be the cube root of 2. In order to get rid of our cube root here, we would love for us to have this b cubed. In some form or fashion, get that b to be cubed. And staying with the same pattern that we use for conjugate, we might as well have this a cubed as well. And let's just add it. So pretty much just cube this, cube that. We know we have no possible ways of having a radical here if we're able to get here. So we start with an a plus b, we substitute that in here. We start with an a plus b, and ideally we want to get to something in the denominator that's like an a cubed plus a b cubed. Well, how do we go from point A to point B, pun intended? Well, now we have to look at factoring the sum and or difference of perfect cubes. Now, if you're unsure of how to do that, I actually have a video on this topic and I'll put it right up here. Check that out and you'll see I have a very easy way of having you remember how to even set this thing up because it is a little bit long. However, if you know those few steps, that little acronym I give you, you'll be able to factor your sum of perfect cubes or your difference of perfect cubes rather easily. So this is how we factor your sum of perfect cubes and your difference of perfect cubes. Are you seeing something that's going to help us here? Well, remember where we're trying to go. We looked into our future. We're trying to get this, an a cubed plus a b cubed. We have an a cubed plus a b cubed. What do we need? Well, we need an a plus b times whatever this is, right? Well, we have an a plus b. So technically, in order to get from point A to point B, all we need to do is multiply top and bottom by this. Whenever you're dealing with the sum of perfect cubes. Now, if it was a difference of perfect cubes, so if this is a minus, then we just multiply by this here. However, we're not focusing on this one because that's not what we're looking at in this question. This question is just needing us to multiply top and bottom by this polynomial. Now remember, the whole point of choosing this to multiply top and bottom is so we know exactly what we end up with in our denominator. So you don't have to waste time doing this math here. You know exactly what it's going to be. It's going to end up being an a cubed plus b cubed in the denominator. That's guaranteed. That's why we chose this. However, up top, you have an a squared minus ab plus b squared. So when you plug in your a and b back into what we have here, you're going to get a squared, which is just going to be a 4, minus a, which is 2 times b, which is the cube root of 2, plus the cube root of 2 squared, which is just going to be the cube root of 4. That's going to be our numerator. Our denominator is just going to have an a cubed, which is going to be an 8, plus our b cubed, which is going to be 2. Notice we can't simplify our numerator anymore because nothing is the same. However, we can simplify our denominator just by combining what these two numbers are. There are no more radicals in there, so we can combine the constants as they are. So our final answer is going to be 4 minus 2 times the cube root of 2 plus the cube root of 4 all over 10. This is our final answer. You have now successfully achieved Super Saiyan 3. So I hope you're following to the examples, and I apologize for saying it might be a short video when actually it turned out to be a little bit longer than I thought. However, if you had any questions about what you saw today or even your own homework, remember, you can always put them in the comment box below or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. If you haven't done so already, make sure you leave a like. It really helps the channel by letting YouTube know that you found this video helpful. And if it's helpful for you, it could also be helpful for somebody else. So leave that like, hit the notification bell, smash the subscribe button, and share this video with a friend. Well, that's all the time I have for today. I really hope this helped with your homework, and I'm looking forward to seeing you again next week. I'm Courtney, and this has been another session of Tutor Me Senpai.